Okay, this is the lecture video for MAC 1105. We're in section 5.4 where we're going to be taking a look at solving exponential equations using all the properties that we discussed in the previous section. Now, the method for solving each of these exponential equations is suggested by the form, so I've grouped them all together for you. Each time I solve an equation that's in a different form that lends itself to a different procedure, I will introduce that procedure to you. So the first group of problems, numbers 1 through 7, you're going to see equations where you can write both sides using the same base. So what this procedure or property tells us is that two exponential equations or two exponential expressions are equal as long as their bases are equal, then their exponents have to be equal as well. So basically what you're going to be doing in these first 7 problems is working to recognize what base do I use so that I can rewrite each side using the same base. Once you get those bases to match, you can work exclusively with the exponents at that point. Okay, the two exponential expressions cannot be completely equal unless their bases match as well as their exponents. So once the bases match, you will work exclusively with the exponents. Okay, now some of these problems will be much fewer steps than the others, and you'll be able to recognize what base to use more easily than some of the others, and some of them you have to do a couple of steps to get there. In this one, this is meant to be the easiest of these problems. You can see that the base here is 2, and I think we're all very familiar with the fact that 4 can also be written using a base of 2. So we can write that as 2 squared. This side is already written using a base of 2. And once those bases match, you can work exclusively with the exponents, which are just x and 2. Okay, once you set those exponents equal, you may have other steps to do to get to the solution. In most cases you will, and sometimes you'll be done as soon as you set the 2 exponents equal. So that is your solution. As soon as you have an equation where x is isolated, you're done with the problem. Okay, in this one you're going to have to do a little bit more. Here you see that this side is expressed as base of 2 with an exponent of 4x minus 12, and this side can also be written using a base of 2. If you look in your calculator, or possibly you just know it, 2 raised to the 4th is 16. So 2 to the 4th is just another way of writing 16, but it allows us to write it in a way such that this base is equal to this base. So again, in numbers 1 through 7, you're working on the skill of writing each side with the same base, then applying the property that says two exponential expressions are equal if their bases as well as their exponents are the same. Once the bases match, you will work exclusively with the exponents to finish the problem. Okay, so these are the exponents, and then if I just add 12 here and add 12 here, I have 4x is equal to 4 plus 12, 16. And then I continue to solve if necessary. This does require one extra step, division by 4, and I finally get x equal to 4 as my solution. So that required a couple more steps than the previous example. Here, this is an example where the base that is shown here is not necessarily the base that you're going to be trying to use on both sides. In other words, this has a base of 64, but can 64 be used as a base raised to some exponent to get 128? I mean, we know 64 to a power of 1 is 64, but even if you go a little higher, you're way beyond 128. So we need to use something smaller. And so it comes into the problems where you have to consider different bases because you may have more than one option. For instance, 64 can be written using a base of 4. See, 4 to the 3rd is 64. But can a base of 4 be used to get this? Well, if we were going to try, it would certainly be a power higher than 3 because 4 to the third gets you 64. So maybe 4 to the fourth? And look, you've overshot your mark of 128. Therefore, we need some base smaller than 4. So let's try 2's. Okay, can we raise 2 to some power to create a 64? 2 raised up to, and you can just try different powers if you're not familiar enough with your powers. There you go right there. 2 to the 6th is 64, so that represents our 64, but that 64 already was being raised to a power. You want to have one base and one power rather than 2. So the way you can mingle 2 different powers is use the rule power raised to another power, which just calls for multiplication. So this is really 2, and now your singular power is 6x. Now we want to see if we can write the other side using a base of 2. 2 to the 6th got us the 64, so it's going to be something higher than that. So I'll try 7, and there you go. 2 to the 7 is 128. Once those bases match, you can discard the bases and work exclusively with the exponents to continue finding the solution. This would require division by 6, and you get as your final solution 7 6's. Don't turn that to decimal form, give it in its exact form. And you don't need to change it to a mixed number. Okay, so here we get to a problem where we have a fraction. So this has a base of 4, and always the base that you're seeing is probably what you're going to think of first as a way to write this other number. However, any number that occurs in a denominator needs to be rewritten using a negative exponent. So values in the denominator must be written using negative exponents. Okay, that'll appear in the work over and over again, so we need to get a hold of that. That when we rewrite things in exponential form, they're written using negative exponents if they are found in the denominator. So this one's already in base exponent form. And this 64, I was demonstrating a second ago that 4 to the third is 64, but since this 64 is in the denominator, it's 4 to the negative third. Okay, again, once those bases match, you can work exclusively with the exponents. Okay, at that point, you're going to want to do whatever steps are left in order to isolate x and get the final solution. I'm going to move the 7 first. I'm going to subtract 7 here, subtract 7 here. I'll continue my solution right up here. So that would get rid of the positive 7, leaving you with just negative x. And here it would be negative 3 combined with negative 7, which is negative 10. Divide off that negative 1 coefficient, and you are into x equal to 10. Any of these solutions can be checked by plugging the original value into the equation. If you were to go 7 minus 10, for instance, you would have 4 to the negative 3, which is 1 over 64. Okay, moving into the next problem. Here, this is a reminder that if you're going to be rewriting things in base and exponential form, that you need to know how to rewrite a radical in power form. Okay, first let's start off with a reminder of that. This is 8 to the x on this side. This side in base and exponential form, it's a 2. It's happening in the denominator, so my power is definitely going to be negative. So let's remind ourselves of that. And then you have to remember how to rewrite a radical. Okay, so you have 2 to the 1 underneath the radical, and the index for a square root is said to be 2. So this 2 in exponential form is 1 over 2. That is how radicals are written. Their power is a fraction. The exponent up underneath the radical is the top of the fraction, and the index is the bottom. However, at this point, the bases still don't match, but that's easy enough to solve because 8 can be written using a base of 2. You can rewrite that 8 as 2 to the third. That 8, which is what the 2 to the third represents, already had an exponent of x, and now you're going to mingle the exponents. You're going to raise a power to a power by simply multiplying. So it's 2 to the singular power of 3x, and over here it's 2 to a power of negative 1/2. We're at the point where our bases match, and so now we can work with just the exponents, which is 3x for one of them, the one on the left, and negative 1/2 on the right. Okay, now to continue, we'd have to divide by 3 to isolate that x, divide by 3 on the opposite side as well. Division by 3 when you're working with fractions is the same thing as multiplying by the reciprocal. It is equivalent. Dividing by any number is equivalent to multiplying by the reciprocal. Reciprocal of 3 is 1 over 3. This number stays the same. And then multiply it out. Top times top, bottom times bottom. And your answer is negative 1/6. Moving to example 6. Here we have a 25 on the left, 625 on the right. It's possible that what you're seeing right here, maybe you can use that to create a 625. If we cannot, we will go smaller. So let's give that a shot. All right, let's see, 25. Let's see what happens when you square. There it is right there. So we can make the bases the same just by going 25 squared to represent that 625. This 625 already had a base of negative 7. And if you're going to have just one power instead of a power here and a power there, then you have to use the power to a power rule to mingle these two powers. That means we're going to be multiplying all of this by 2. That's how you mingle two powers and combine them, through multiplication when you're raising a power to a power. So it's going to be 2 times x, 2 times negative 7, and then this was already 25 to an exponent of x plus 2 when we started. Okay, we're now at the point where these bases match, and therefore we can exclusively move to the point of the problem where we work just with the exponents. So exponent on the left is x plus 2, and the exponent on the right is 2x minus 14. Okay, so now steps required for solving. Get all the x's on one side. You can either get them all over here or all on the right. I'm going to move all my x's to the right. Doesn't matter what side you move them to. I just wanted mine to be positive. It's just my choice. Okay, so you have all the x's on the right. 2x minus 1x is positive x, and therefore I need to move this negative 14 over here. Moving that negative 14 is the same thing as adding 14 on both sides. 14 plus 2 is 16, and that's your final solution. Okay, moving to example 7, the last of our group of problems where we are working on getting each expression rewritten using the same base. Okay, this is in a base of e, therefore we want this to be base of e to an exponent, just like this is. So this is e to the power of 1, but since that e to the power of 1 is happening in a denominator, it can be written in base and exponent form as long as you remember that anything in the denominator must be rewritten in exponential form with a negative exponent. This one already had base of e and exponent, have those bases being the same. Therefore, we can just work with the exponents, which is x plus 1 on the left, negative 1 on the right. Okay, going to the steps for solving. To isolate x, just subtract 1, and you get x is equal to negative 2. Okay, now we move to a different form where we will be using a different procedure in order to solve the problem. We're still going to be looking at problems where you'll see a base and an exponent, only it will not be possible to rewrite the other side using the same base, therefore the need for a different procedure. So if you're going to try and isolate this exponential expression, this is how you can handle these problems where it is not possible to rewrite the other side using that same base. You're going to take the log, the common log of both sides, if it's a base of 10. And let me highlight that for you. Okay, so we move into the problems in numbers 8 through 12. We're taking the log of both sides. We're going to give an exact answer each time as well as an approximate answer using our calculator. So since there are two kind of logs, we're going to take a common log, log, if the base is 10. We will take the common log of both sides, this kind of log. Okay, if the base is anything other than a 10. Anything other than a 10, you're going to take a natural log for any base other than 10. Okay, I'll remind you each time we do the problem. Again, these problems in numbers 8 through 12 are all about the impossibility of rewriting one of the sides using the base that you're seeing on the other side, and therefore the need for taking the log, either common log or natural log. So when the base is a 10, just like it says right here, we're going to use the common log. Common log is log. Okay, so we're going to take common log here, common log here. Maybe I can write that out a little nicer instead of trying to squeeze it in. Okay, when it says to give an exact answer, that's before you press it into anything into the calculator. Okay, so I want to remind you of some of the properties. The previous section, section 5.3, was all about the properties that can be used to simplify logarithmic expressions. This is one of them. When you're talking common log, the base is said to be 10 for common log. Okay, when the base matches the argument, that is an application of the inverse property from the previous section. Argument matches the base, they cancel, take the log with it, and down comes the exponent. So this problem turns into x is equal to log of 2.88. This is what we mean by an exact answer. And you'll have to see whether or not you'll see by what kind of answer blanks they're offering you, and Mom, whether they want you to put the x is equal to, but probably not. It'll probably just be log of 2.88. Okay, that's the exact answer. Haven't pressed anything into the calculator. Approximate, now put it in the calculator. So now it's just going to be log 2.88 and round to whatever they've asked you to. In this one, in these directions, we're going to be rounding to 4 decimal places. That would be 0.4594. Okay, so this represents an exact answer, just log of 288, and this represents an approximation of log of 2.88. Okay, moving to this one. Now remember the directions. Let's go back up to the directions that you're going to take a common log on both sides if the base is 10. But for bases other than 10, you will be taking a natural log of both sides. Okay, so this is going to be ln of the left, ln of the right. Natural logs have only one base, and that is e. Right? And you can, when you do rewrite when you give your answer, you can write it without the base. I just wrote it like this because I want you to understand that the inverse property also works in this particular example, just like it did in number 8. See how the argument matched the base? Same thing here. Argument matches the base. They take each other out, take the natural log with it, and down comes the exponent. When you go to give this side, you don't have to write the base of e. I was just trying to be explicit here so you would. It's optional, but you can write it if you'd like. Okay, so this, what you're seeing right here, represents the exact answer. And then an approximation, ln of 14.48. Close that up. Going to 4 decimal places again for all of these, so 2.6728. They're going to be asking you to do that in the homework as well. Give an exact answer and an approximation. All right. Moving to example 10. Okay, so again, you cannot rewrite an 83 using a base of 11, thus the need for this new procedure where you're taking the log of both sides. Directions said if the base is 10, you'll take a common log of each side, and for all other cases, take a natural log. So this will be natural log of 11 raised to a power of x, natural log of 83. Okay, and you can write that base or not. I didn't write it this time because they don't match anyway, but of course you can. You can put that base in there. It's optional. Notice that these don't match, so I can't just cancel this out with this by using the inverse property because it doesn't apply here. But you did have another rule that said when you have 3 levels, the base, the argument, then the exponent, then the power property for logs is what goes into play here to simplify this. Exponents on log expressions, they become coefficients. So from the previous section, one of the properties that we learned. So ln of 11, and you can use that e, write that base of e or leave it off. That's up to you. It's just easier to write it like this. Okay, let's keep going because we don't have x by itself yet. It is this x is being multiplied by ln of 11, so divide by ln of 11. Whatever you do to one side, you're going to have to also do to the other side. It'll cancel here, leaving you with x is equal to, in its exact form, ln of 83, and it's called an exact answer because you have not turned it into a decimal yet. So this is the exact answer, which goes right here. And then if you want to go and put it in the calculator for an approximate answer, it would be ln of 83 divided by ln, and let me do that again. Okay, so ln of 83, let's go ahead and close that up, divided by ln of 11. And that gives me 1.8428. For an approximate answer to the 4th decimal place. Okay, moving to example 11. Let's see, so we have a base of e here. We will eventually be taking a natural log, But you want to always isolate your exponential expression first. Get the base and the exponent by itself before taking the ln or the log of both sides, depending on what kind of log you're going to take. So, to remind you of that, always isolate the base raised to its exponent before taking the ln of both sides, before taking the log of both sides. So I'm going to divide by 7, divide by 7. I'll then have e to the x is equal to 59 over 7. Don't approximate. Don't put anything in the calculator until we go for that approximate answer. We want to keep everything exact while we're on our way to giving this answer right here. So now, because this is a base of e, we're going to take, remember it said anything other than a base of 10, take a natural log. So we're going to take natural log here, natural log here. Remember, that base is e, whether you choose to write it or not. Writing it will maybe help you to focus on the fact that this argument matches this base, therefore they cancel. Take the natural log with it, and all you have left on that side is what's in the exponential position. On this side, you just have 59 over 7 as your exact answer. Decimal approximation of that, just press it in the calculator. So it would be ln of 59 divided by 7. And that is 2.1316. 2.1316. Okay, moving to this side. This is another example of where we're going to be taking a natural log because you see that the base is something other than 10. You only take common log when the base is 10. However, as I stated in this problem right here, before you go taking the log of each side, you want to isolate the base and the exponent. You don't want any other terms other than the base and the exponent. Therefore, I'm going to move this 7 by adding 7. Okay, that'll give me e raised up to a power of 2x minus 5. And then here I'll have 2, 5, 7 instead of 22, I'll have 29. Once you have the base and the exponent isolated, then you're going to take your log of both sides. So taking natural log here, taking natural log here. Again, that base is e on a natural log, therefore this cancels with this, taking the natural log with it. Okay, on the other side, you don't have the inverse property working for you. That base is e, but yet the argument's 25729. So you leave it like this in its exact form, natural log of 25729, and then we'll continue up here. We are trying to isolate for x, which is going to require 2 more steps. We're going to have to add 5 and add 5. So on this side, the negative 5 cancels with the positive 5, leaving you with 2x, almost there. And over here, you have ln of this argument, 25729. Do not try adding the 5 into this. That's a really common mistake. Plus 5. So this was its argument. And then it just has 5 added, and then we're going to be dividing by 2, dividing this side by 2. So this cancels, leaving you with ln of 25729 plus 5 divided by 2. And then you press it into your calculator exactly like that. So this would be your exact answer. Okay, putting that in the calculator. Okay, that'll be ln of 25729. Close that. plus 5, got my numerator, divided by 2. To the fourth decimal place, it would be 7.5777. 5.5777. Okay. Moving to another form of problem. So after we get through with number 12, we've left the problems where you need to take the log of each side. Notice how these problems looked in the previous set of problems, so you can see how these are different. Notice that all of these start off with a log in the problem. So it's a different technique. Based on the form that the problem is presented to you in will determine the technique that you use. Okay, first 7 problems, we were able to write each side using the same base. Then we came to numbers 13, we came to numbers 8 through 12. We were not able to rewrite each side using the same base. But notice that none of these problems have the word log in it until we introduced the log into the problem as the technique for solving. These are starting off with one log, single log in the expression. Technique for that is written right here above. This came from the section where we learned how to rewrite logarithmic expressions as exponential expressions. When given a log, if you want to rewrite it, take it out of log form, which is what you're going to do. You're going to bring it to exponential form, as you're doing with anything that you can do that with in this section. By raising that base, it's still the base, but it's going to be the base of the exponential expression. Raise this up, go grab the number that's on one side all by itself. It will be, or the expression that's all by itself on the opposite side of this log base. It will become the exponent, and this value, this argument value, will jump in its place. So that's the skill we're going to be using anytime we have a single log on one side. And sometimes we'll have the ability to create a single log and we'll still be able to apply this property. So if it's possible to have only one log, no other logs on the other side, because then we're moving into a different technique, we are going to go from log form to exponential form using this definition that I just showed you. Push up the base. Go grab the expression that's on the opposite side. It will become the exponent, and this m jumps over. This argument jumps over and takes its place. Okay, so doing that, we're going to push up this 7, go to the opposite side, and go grab that value. It will become the exponent, and this jumps over and takes its place. So these two values switch sides. We sometimes call that round robin. The 2 came over here, acting as the exponent, and the x went to the opposite side, taking its place. Okay, so what is the exact answer? X equal to 49. Okay, when it says give an exact answer, that just means don't give a decimal approximation. So I believe you're going to be giving them without the x when you feed it in. So approximate answer, there is no approximate answer. I mean, if you had to give this to 4 decimal places because they give you a space to do that, you can just write it like that. Okay, moving now to the next one, example 14. Example 14, you know that when you have a natural log, no base shown, the base is said to be an e. So if you're going to put that in the form where you're taking it out of log form, which is the general technique for numbers 13 through 25, we're just going to raise that up, that base, go to the opposite side, go grab that value. It will become the exponent, and this argument of the log jumps to the other side and takes its place. So this would be the exact answer. whereas this would be the approximation. So it'd be second, call up e to the x, and then feed in the power. And that would be to the fourth decimal place, 7.3891. Okay, moving to number 15. Okay, in problem 15, we're going to be doing log of x plus 8, base of 7 equal to 2. So single log on one side, no log on the other side. Using this technique, we're going to push this up to put it in exponential form. It'll still be the base, but of an exponential equation. This will become the exponent. And this entire argument jumps over and takes its place of the value that was on the opposite side. Okay, so now we just end up with an equation. We don't have an exact answer yet, where we still have a couple of steps. We have to realize that's 49, what's on the left, and we also have to move that 8. Isolating the x and bringing us to 41. This is an exact answer. They say give it to 4 decimal places as an approximate answer, it would be like that. Okay, moving to number 16. In number 16, we have log of x plus 4, base 4, and a negative 4 over on the other side. So just as we've done in the last few problems, we're going to take this out of log form by raising up that base and allowing it to be the base of an exponential expression, going to the opposite side to grab the exponent, and letting this entire argument jump over and take its place. That is rewriting from log form to exponential form. We now have no log and we can isolate our x. So let's see. We'd have to first realize what 4 to the negative 4th is. And we want to keep everything exact, so no decimal approximations. Okay, you can just say, you want to keep it exact. 4 raised to the 4th is 256. But since it's negative, that means it's 1 over 256. And then here it's x plus 4. Okay, and if you want to continue, then it's subtract 4. Subtract 4. So it would be 1 over 256 minus 4 is equal to x. Now, you can still get an exact answer as long as you're not giving a decimal approximation where you're chopping off some of the decimals. So to keep this exact and in fractional form, then you have to know how to press this in. It's just a matter of pressing it in. 1 divided by 256 minus 4. Let's see what happens with this. No. Okay, so 1 divided by 256 minus 4. And if you hit math, enter, enter, it'll take you to exact fractional form. So in the middle, it'll take you to a decimal, even though that's an exact representation of 1 over 256. But you just don't want to do any rounding when it says give the exact answer. So I went 1 over 256. I mean, I could have put the whole thing in the calculator at one time. So we got 1023 for our answer, negative 1023 over 256. I just want to demonstrate that you can press in the whole thing like this. This over this without figuring out what the decimal value is first, then minus 4. It's just that you have to hit math, enter, enter, instead of just simply pressing enter. That'll give you a decimal, and then you're going to be tempted to round it off, which you should not be doing. So let's do that again. 1 divided by 256 minus 4, math, enter, enter. See? Negative 1023 as the numerator divided by 256. Okay, so that is your exact answer. Then if you are going to get a decimal approximation, then negative 1023 divided by 256, and then just press enter. Don't hit math enter, and you will get a decimal. And then you can round it off. So this is negative to the fourth decimal place, 0.9961. Negative 3.9961. Okay, this is the decimal equivalent of this, rounded to the fourth decimal place. Moving to number 17. Okay, in problem number 17, we're looking at log of 6x plus 9 is equal to 5. And in this problem, we're going to be raising this up to get it out of log form. Again, you will use this technique if you have a single log on one side, no log on the other side. Okay, so 2, go to the side where you have an expression or value by itself. It will become the exponent. And then this entire argument jumps over, takes its place. And then you'll go through whatever steps you need to go through in order to isolate x. So right now I have 32 is equal to 6x plus 9. I'm going to subtract 32. Whoops, no. I already have the 32 over here, so might as well get this over where the 32 is. I'll just leave the 6x over on the right. And then on this side, if I'm going to take away, if I'm going to go 32 minus 9, I'm going to be left with 23. Okay, and then you're going to divide by 6, divide by 6. And you get x is equal to 23 over 6. Okay, that is your exact answer. And then decimal approximation will be 23 divided by 6. You can just hit enter to let it give you a run on the decimal, whatever decimal equivalent there is, and then you can round it off. So 3.8333. Okay, moving to number 18. In problem number 18, again, we have a single log. However, the single log is not by itself. You don't want to rewrite. Let me write this a better way. You are to isolate. Isolate your log or ln expression before rewriting in exponential form. See, right now there's too much over here. You need to move the 3, you need to move the negative 7. And with these problems where you have a log or a natural log in the problem, we actually need to think about the final answers that we're given, because you have to reject any kind of answer that makes the argument of any of the logs in the original problem. You need to reject any of those because there's no such thing as the log of a negative value, or of 0 for that matter. So you need to go back and check those. We'll go back and check the ones that we've done by this method just to make sure that that we didn't report anything that makes the argument negative or 0. Okay, so let's just continue with this one. In this one, we're going to move 3 to the other side. Then we'll have negative 7 is equal to negative 1. Then we're going to remove the negative 7 like that. And then we will have ln, oops, we'll have ln of x is equal to 1/7. Okay, and then now you can rewrite this in exponential form. Okay, once you get the log expression all by itself, no multipliers, nothing being added or subtracted, then you can go into exponential form. So the base is e here, so that's the base that we're going to be pushing up. We're going to be attaching this as the exponent and letting this argument take its place. So that's the answer in exact form. This happens to be a positive number, and if you plugged it right in there, it would not be a value that you need to reject. Whatever you're getting here, it can't be a value that's 0 or negative. So that argument value needs to be greater than 0. It cannot be 0, and it cannot be negative. We'll go back and check the answers that we have gotten thus far within this particular technique. Okay, so let's go e to the 1/7. So we're going to go second function, call it the e, feed in the 1 divided by 7, and that would be 1.1536. 1536. Okay, let's go check out the other answers that we've gotten using this technique. So let's see, I think these started back on example 13, where we were getting answers that belonged to problems that were originally written in the log form. These are the ones that you have to reject any value that is not in the domain, which means, what does that really mean? Rejecting any value that is not in the domain. It just means that the answer that you get for x, that value, which is also known as the argument, has to be greater than 0. See, when you take the log or the ln of 0, see, that's not in the domain. If you take the log of 0, same thing. Likewise, if you try to take the ln or the log of a negative value, see, nothing. You may not use negatives or 0, so be careful with that. This e squared, that's a positive number, so it's okay there. It would not violate that argument. It is in the domain. Oh. Shh. So sorry. So sorry about my dogs. Just a minute. So sorry. Okay, so we were checking these answers that we've gotten. Okay, we got a 41 for example 15. Notice that when you put it right in there, it doesn't make the argument 0, nor does it make it negative, so that was okay. This answer that we got here, this one might be a problem, but maybe not. It's not all about it just because it's negative, you throw it out. That's not what we're saying. We're saying, and so I should rewrite this in the most efficient way possible. This is the best way for me to write it. That argument better not be 0 or negative. It must be greater than 0. So when we're looking at checking number 16, let's see, yeah, 16 is what we were checking. When you go and put this value, look at the value that we got right here. We got negative 3.9961. Well, when you go and plug that in right there, negative 3.9961, and then add 4, you end up with a positive argument. So the argument in this particular problem, negative 3.9961 with 4 added to it, because that's the entire argument. this is bigger than this, bigger number is positive, therefore that argument is greater than 0. So you're actually okay there. So just because it's negative, don't throw it out. You want to make sure that it's not something that should be rejected for the argument. This right here, positive number, so multiplying it by 6 and adding 9 is still going to be positive. So we were fine there as well. In example 18, we already talked about how this argument value is greater than 0. And then moving to number 19, we have log of x plus log of 10x minus 1 is equal to 1. And so for the first time in this problem, we actually have 2 logs, but no log on the other side. The key is not to have log on both sides, because then you're jumping into a different method for us solving, and we'll get to those. Remember that in the previous section, we did learn how to condense 2 logs into a single log. Specifically, we studied that if there is a plus sign between 2 individual logs, that means that they used to be a product. So this particular log here, both base 11, as long as their bases match, you can apply these properties. What is 2 logs joined by a plus sign? They used to be a product in their arguments. Their arguments should be multiplied together when bringing them back together as a single log. So the entire argument now is this, is equal to 1. Okay, if you want to put this in exponential form, just like we've done all the way up through example 18, I believe it was 13 through 18 so far, I'm going to raise up that base, go grab the value on the other side, and then this entire argument jumps over in the place of that value that you just used as the exponent. So x times 10x minus 1, this would be 11, is equal to 10x squared as you distribute that x into the parenthesis, multiplying it by 10x, that would give you 10x squared. Then x times negative 1 would be negative x. Okay, then you can bring everything to one side since it is second degree. In other words, subtract 11, subtract 11. And you would have 0 is equal to 10x squared minus x minus 11. So second degree, one of the top methods for solving that, the main method for solving that has been factoring, and when factoring will not work because you can't come up with the number combinations, then you can move to quadratic formula. So let's see. If we try to break this up, we could try 2 different things. We can try splitting the 10x squared up as 10x times x or 5x times 2x. Let's just see. That's why one of the methods for factoring a quadratic trinomial, quadratic means second degree, is called guess and check, because you have to guess at how to break up this term to fill in the front 2 spots and also how to fill in the back 2 spots. So let's try 10x and 1x. If it doesn't work, we could always go to 5x and 2x. Okay, if we're going to need an 11, if we're going to use an 11, if we're going to break down an 11, that only way you can break down an 11 is 11 times 1. You put the 11 back here and you're going to get a big number, because foiling is the way that you check whether you have split these things up properly as you factored it. So let's just keep the 11 here and the 1 here, okay? Breaking up the front term requires what 2 factors multiply to give us that. Putting items in the back 2 spots is breaking down that back number. Now let's get the signs right. We want our middle term to come out negative. Therefore, in that process that we use to check our factoring called the foiling process, we would have first times first, that would be positive 10x. 10x times x, that would be 10x squared. That would get you that. And then 10x times 1 would be positive 10x if we put a positive back here. But if we put a negative here, we'd have 11x. So positive 10x minus 11x would give us the proper sign on our middle term, and it would give us a negative 11 back there. So knowing how to FOIL will help you see whether you have put things in the right place and whether you've given them the right sign when you're going to use the guess and check factoring method. You can also factor this by a method called splitting the middle term, which I've demonstrated quite a bit. Okay, so this is all factored, and now we're going to make two tiny equations, because if this is second degree, that means we're going to get two answers. Not that necessarily both of them will be valid answers, because remember, we have to reject solutions that make the argument 0 or negative. So 10x minus 11 is 0 will give us one answer. X plus 1 equal to 0 will give us another answer. Sometimes you can just eyeball the factor and tell what makes it 0. In this case, yes, negative 1. Minus 1 would be negative 1. In other words, negative 1 is what makes this factor a 0, and therefore this is the value 1 is considered a 0 or a solution of the equation. Here, finding the 0 for this factor, maybe you should just go through the steps for solving it, since it requires two steps. Move this negative 11 to the other side, it'll be positive 11. You would then have 10x equal to 11. Divide by 10, and you get x is equal to 11/10. Now, are both of these solutions valid? Are possibly neither one of them valid? We have to check to make sure that we are not creating a 0 or a negative in our argument. Okay, 11 over 10. Maybe you want to think about that as a decimal approximation just to see whether it's a valid answer. 11 divided by 10 would be about 1.11. Okay, so 10 times 1.11, because that's what we got for one of our answers, minus 1. Is that negative? It's not negative, it's not 0. So this answer is good. How about this answer? If we put a 1 in there, we would have 10 times 1 is 10. 10 take away is 1. 10 take away 1 is 9. That's a good answer. You must check them when your original problem has a log in it. Not only that, you have to check both expressions. So I just found out that 11 over 10 was good here, and the number 1 is good here. But is it also good here? Because if it destroys either one of these log values, in other words, if it makes the argument 0 or negative in either one of them, it's no good. 11/10, that's positive, so if you put it right there, the argument would be positive. We're good. 1, if you put it right in there, the argument would still be positive, and it wouldn't be 0. So both of those answers are good. I checked both of them to make sure that they didn't create a 0 or a negative here, nor did they create a 0 or a negative there. So we report both of them. But sometimes we have to get rid of one of them, or we have to reject both of them. So exact answers, 11/10 and also 1. Approximate answers, well, we saw that this was 1.11. If it says to do it to the 4th decimal place, you could just write it like that. And the 1 could also be written like that, to the 4th decimal place, if they ask you for an approximate answer. So I'm going to stop this video there. We still have 10 or 11 problems left to do, which are other techniques for solving logarithmic equations, as well as some application problems. And I'm going to put those from numbers 20 through 29, I believe it is, in the second video. Okay, so that completes part 1 for section 5.4, numbers 1 through 19.